Okay, so here we are at the Krebs cycle, and we had talked about how yesterday glycolysis is broken down into 2-pyruvate. If I were to ask you today to tell me what the purpose is and what is generated from glycolysis, could you tell me the purpose of glycolysis off the top of your head?
The production of the electronic separating ATP.
Yeah, the big thing is the production of NADH, which is going to, remember, each carries 2 electrons. That goes to the third step, which is the electron transport chain. Part of it is the electron transport chain, where the majority of your ATP is made. In that process, so to get those NADH made, glucose is broken down in this series of steps, stripping electrons from molecules that used to be glucose, and those electrons are now in NADH. In that process, we make 2 ATP, right? And is that enough to keep the cell alive? No. All right, so therefore we need to get to that third step to make our ATP. Then remember, pyruvate goes through that link reaction where it's converted into 2 acetyl-CoAs. In that process, 2 carbon dioxides are released. So we take off a carbon dioxide out of pyruvate and add in the acetyl, or the CoA part, and it becomes acetyl-CoA. And in that process, 2 NADHs are made. And so we have now 4 NADHs coming from the first kind of 2 steps in cellular respiration, going to the electron transport chain and carrying electrons there. So then here we are now with the 2 acetyl-CoAs entering the Krebs cycle, or the citric acid cycle. And did I ask this yesterday? Why is this called a cycle? Did I talk about that? No. Somebody tell me, why do we call the Krebs cycle? And I just have a series of arrows here to show you it's the cycle here. This is the actual molecules here. Can somebody tell me why Krebs is called a cycle? Glycolysis is not. Glycolysis is not a cycle. Citric acid cycle is a cycle. What makes it a cycle? Olivia? That's right. At the very end, where's the end of the Krebs cycle? How do I know where the end is?
At the top.
Up here, the end is oxaloacetate, because here's your acetyl-CoA. That's the acetyl-CoA coming from the link reaction. So that's the beginning. So the beginning here is the acetyl-CoA and oxaloacetate reacting, forming citrate, and we go through a series of reactions, and as Olivia said, you end up with, at the end of the cycle, with the same molecule that you started out with to begin the new reaction and so on. So citrate is the first molecule that's actually made in the citric acid cycle, and then you regenerate your oxaloacetate that can meet another acetyl-CoA, and so on and so forth. So that's why it's a cycle. Now you do not need to know, and that's why I just put the little arrows here, you don't need to know the names of these guys here, so that you don't have to memorize that for this class. We just kind of need to know the big picture as far as what happens in the Krebs cycle. Also, you should be able to look at a picture of the Krebs cycle like this with the names and answer questions about it. So there might be diagrams, like on the test or on the AP test, in which you need to be able to interpret, and so this would be something that you would do, although you wouldn't be asked to memorize these things. All right, the intermediates. So, so the Krebs cycle. Let's talk a little bit about that, and then we'll add that onto our picture here. So let's go over the answers here. So where in the Krebs cycle, or where in the mitochondria does the Krebs cycle take place? It's in the matrix of the mitochondria. The matrix is the fluid inside of the mitochondria. Then I asked you what molecules introduced to the Krebs cycle from the link reaction. You should have acetyl-CoA, where it comes in. Is oxygen needed as a reactant in this? If you look at here, the answer is no. How do I know oxygen is not needed as a reaction? Because there's no O2 with an arrow going in anywhere. So there's no oxygen. So far, oxygen is not used at all. If we look at the big picture on the top of the board there with the equation for cellular respiration, Oxygen is a reactant, so is glucose. Those are your only two there. Oxygen has not been used at all yet. All right, so in glycolysis, the link reaction, or now the Krebs cycle. So then it says to compare the oxaloacetate molecule with the citrate molecule. How many carbons are in the oxaloacetate molecule? You should have counted 4 there. And how many carbons are in citrate? And there are 6. So carbons just don't come out of nowhere. So see, actually, where do those carbons come from to make from a 4 to a 6 carbon compound? And that comes from the acetyl group, the acetyl part of the acetyl-CoA, because the CoA doesn't become part of citrate, it leaves. So it's the acetyl part of that molecule. And it's a 2-carbon compound, and that makes up for the 2 carbons there. All right, next page. I'm going to leave the picture up here so I can look at this. Next page here, 20, compare the citrate molecule with the alpha-ketoglutarate molecule. And so that's this one, so citrate compared to this one here. It says how many carbons are in, A says the alpha-ketoglutarate, and that is 1, 2, 3, 4, 5, right? And the citrate had 6, right? So going from 6 to 5, where did that go? The carbon was released as CO2. And then number 21, compare alpha-ketoglutarate to succinate. How many carbon atoms are in succinate? And so it's 1 less again, and so now we have 4. And we had 5 here. So where did that carbon go? It left as a CO2 molecule. Then 22 asked you, through the Krebs cycle, energy is transferred to other high potential energy molecules. List those molecules and indicate the number produced with 1 turn of the cycle. So the other high energy molecules that are produced are NADHs, and there's 1, 2, 3 produced. Another one is ATP. There's 1 produced with 1 turn, and the other energy molecule that's made is FADH2, and there's 1 of those. All right, with 1 turn. So then number 23, which molecules in the Krebs cycle has the highest potential energy? So which one of these has the highest potential energy, and give evidence? Somebody want to tell me what you thought there? Which one had the highest citrate, alpha-ketoglutarate, succinate? Ellen?
I thought that it was citrate because it's not broken down to any of the other molecules, and like no molecules are coming off of it yet. And so like, in addition to that, there's no heat loss as well, so I thought that had the highest.
Okay, you're right that this is has the highest potential energy. And if we look here, as citrate is converted to all these other molecules here, what's made in the process? NADH, ATP, FADH2, NADH. So what happens is these are, when NAD plus becomes NADH, NADH has higher energy than NAD plus. Where does that energy come from? It's not, energy is not created, it doesn't come out of just nowhere. Where that energy came from is when citrate is converted to alpha-ketoglutarate. Alpha-ketoglutarate is a lower potential energy. Why? Because some of that energy went into making NADH. Does that make sense? All right.
So they still have the NADH molecule?
So the NADH, the energy that was once in citrate, some of the energy is now in NADH. Some of that is in alpha-ketoglutarate. So alpha-ketoglutarate has less energy because some of the energy in citrate went to NADH. Does that make sense?
So like you could say like they still have the high potential molecules intact. They haven't produced NADH or the FADH.
Right, citrate. Yes,
Yes.
yes. All right. And then if we look at the next from alpha-ketoglutarate to succinate, alpha-ketoglutarate has more potential energy. Why? Because as that converts to succinate, some of that energy is now embedded in NADH and ATP, so this is lower free energy. Oxaloacetate has even lower free energy. So therefore, that leads us to number 24. What molecule in the Krebs cycle has the lowest potential energy? That should be oxaloacetate. All right, because in that conversion, as we go around the turn, a lot of that energy was used to create these high energy molecules, NADH and ATP. Okay? and so that's the lowest free energy. So then 25, considering your answers to the previous 3 questions, what can you conclude about the potential energy of the acetyl group that is carried from the link reaction to the Krebs cycle by coenzyme A? Does this group of atoms have high or low potential energy, and explain your reasoning? So look at here, let's just look at, you have acetyl-CoA, the acetyl group is bound to the CoA, the coenzyme group. And that comes in and reacts with oxaloacetate. We just said oxaloacetate has the lowest free energy in this mix here. Alright? But then look at here, when it binds and reacts with acetyl-CoA, it forms citrate, which we just said has the highest potential energy in the whole cycle here. Where does that energy come from? All it did was oxaloacetate reacted with the acetyl group. CoA doesn't bond, doesn't react, that's released. So the acetyl group reacts with oxaloacetate to form citrate. All of a sudden now we have a really high energy molecule. So therefore the acetyl group would be high or low energy? High energy, all right? If it was low energy, you'd end up with a low energy molecule, and that's not what we get. We get a higher energy molecule, so, and we said that this was a lower energy molecule, so therefore the acetyl group must have high potential energy. So then 26, how many turns of the Krebs cycle occur for every glucose molecule that undergoes cellular respiration? Well, how many acetyl-CoAs are made for each glucose? We have 2. So therefore there are 2 turns to this, all right, for every glucose molecule. Then 27, how many of each of the molecules below are produced in the Krebs cycle of every glucose molecule that undergoes cellular respiration? So if we look here, for 1 turn, you have for CO2, 2 CO2s made, but we just said that there's 2 turns, so therefore you have 4 CO2s made. ATP, for 1 turn there's only 1, so multiply that by 2, so that's 2 ATP. NADH, there's 1, 2, 3 for 1 turn, so your total should be 6. And FADH2 is 1 for 1 turn, so your total should be 2. And then lastly, 28, was oxygen used as a reaction, or a reactant, and any other processes explored in this activity so far? Glycolysis, link reaction, or Krebs cycle? No, your answer is no there. So far, oxygen has not been used at all in this whole cellular respiration process up through the Krebs cycle. So glycolysis, link, and citric acid cycle. All right, so therefore oxygen is going to have to be used. It's a reactant. It's going to have to be used in this oxidative phosphorylation. All right, so so before we go to the, I still have the extension questions, don't I? The extension questions, I almost was going to move on to the oxidative phosphorylation. Let's go over those. A lot of people in looking at these had trouble with these, so let's look at them. So number 29 asks you to identify 2 places in the Krebs cycle where a decrease in free energy is coupled with an increase in free energy. So let's go back to that picture of the Krebs cycle. So when we look at, erase my writing from last hour. So if we look at, let's just look at the beginning here. Here we have acetyl-CoA coming in and reacting with oxaloacetate to make citrate. So we said that this had low potential energy, this had higher potential energy. And so what we have here, if acetyl-CoA comes in and the acetyl part reacts with oxaloacetate to form citrate, and the CoA is released, from here to here, we've gone from a high potential energy molecule, the acetyl-CoA, and the acetyl group now came in and reacted with oxaloacetate, leaving behind coenzyme A. The coenzyme A now has a lower potential energy than it did as acetyl-CoA, and that acetyl-CoA, the acetyl group, when it bonded with the oxaloacetate, created a higher energy molecule. So notice here when it asks here we have a decrease in free energy in this reaction, and that created an increase in free energy when we go to oxaloacetate to citrate. So this is a higher, I should say, potential energy there. So therefore, this became lower, decrease in potential energy, increase in potential energy. Do you see where if a molecule increases in a reaction, if you get your product, which is citrate here in this reaction, has a higher potential energy, that energy has to come from somewhere. And so that energy, you have another molecule that decreases in potential energy so that another molecule can increase in potential energy. So that's one example. So the acetyl-CoA to coenzyme A decreases, and then oxaloacetate to citrate increases. We can do that for every single one of these. If you notice here, citrate to alpha-ketoglutarate. It makes a higher energy molecule, NADH. So therefore this goes from higher to lower free energy. Where did the energy go? The energy now is in NADH, so NAD plus had lower and went to higher potential energy. So therefore some of the energy in citrate went to NADH, so this increased in potential energy, so therefore your alpha-ketoglutarate lowers. And then we can do the same thing. So this has a higher free energy or higher potential energy than this. All right, and so that decreases, and NAD plus and ADP increases in potential energy as it becomes NADH and ATP. So therefore, there we have a coupling reactions decrease with the increase of potential energy. So any one of these reactions would be an example of that. All right, so then let's go back here to 30. So let's just read the stem of the question. It says, when the body runs out of readily available carbohydrate or glucose molecules, it will turn to stored glycogen, then fats, and finally proteins as an energy source. So the pathways below illustrate how these molecules are prepared to enter the cellular respiration pathway. So we're going to look at this and compare it to our big picture here to see where these guys end up with. So remember, if you eat too much glucose, back to chapter 5, that we store our excess glucose as glycogen. Glycogen, remember, is a chain of glucose molecules. Where do we store the glycogen at in our bodies? Do you guys remember? Muscle and liver. And so that's our excess glucose storage. So what happens is, if you are not eating, your body has stored glucose as glycogen in your muscles and in your liver cells. So what will happen is, if your blood glucose levels, glucose is floating around in your blood, if your blood glucose levels drop because you're not eating and therefore your cells the glucose is going out of your blood into your cells to be used in cellular respiration for energy, what will happen is that drop in blood glucose will trigger your liver to start breaking down glycogen. And so what this is showing you here is glycogen is broken down into glucose because it's a chain of glucose. That glucose now enters your blood sugar rises, and the glucose can go to your cells and be used for cellular respiration. So when this happens, when your body starts to break down glycogen and release glucose into your blood, glucose enters this process of cellular respiration at what step? Glucose enters cellular respiration at what step? Glycolysis, right? So, so down here for A, when it says, for each of the products above, including urea, identify the phase of cellular respiration where the molecules would enter the cellular respiration process. And so glucose enters it right at the beginning at glycolysis. So that's what you want to put here. So glucose enters it during glycolysis, and at the very beginning of glycolysis. Now, what happens next is, if you still continue to not eat and not bring in glucose, your body will use up its stored glycogen and then move on to breaking down fat. So fat is stored when we eat excess fat or excess, actually glucose that can be converted to fat. We store fat in special cells called adipose cells in our body, usually around our middle. And that fat stays there until we need it for energy. And so when you need it for energy, remember again from chapter 5, a fat molecule looks like the letter E. There's 1 glycerol and 3 fatty acids, all right, attached. So that's why it says here 1 glycerol and fatty acid times 3. So when we break down our fat molecule into those things. Glycerol, there are enzymes in our cells that can convert glycerol into pGal. Glycerol itself is not used in cellular respiration, but pGal is. Where's pGal in cellular respiration? This is in glycolysis. It's after that first energy investment phase right here in glycolysis. And so pGal also is used during and enters in glycolysis, and then you can finish glycolysis and go through the rest of cellular respiration to get your ATP. Then also in that fat molecule there are fatty acids. Remember fatty acids? Why it's an acid is it has that carboxyl group attached. And then remember it's a hydrocarbon chain. So carbons, and what makes one fatty acid different than the next is how long it is, if there's double or single bonds, and so on. So that's your fatty acid chain, and there's 3 of them. So notice here, fatty acids never enter directly into cellular respiration, but what happens is that our cells can convert fatty acids into acetyl-CoA. Acetyl-CoA enters where? It's going to enter the Krebs cycle, right? That's the molecule that enters the Krebs cycle. So for acetyl-CoA, this is the Krebs or citric acid cycle, whichever one you put there. Let me point out that it says the number varies but numerous. So what that means is there are 3 fatty acids. Every fatty acid is different in length. One fatty acid doesn't make, it's not a 1-to-1 ratio where one fatty acid makes 1 acetyl-CoA. One fatty acid can make many acetyl-CoAs. And so therefore, because fatty acids are different in their length, some are longer, some are shorter, and so on, every fatty acid makes different amounts of acetyl-CoA. So that means that from that 3 fatty acids, there's three of those hydrocarbon chains. Each one of them can make many acetyl-CoAs, so therefore you have numerous acetyl-CoAs. And so if you think about this, then from one fat molecule, you can get a lot of ATP, just one fat molecule, glycerol, converted to pGal. So you're going to go right here and go through this part of the cellular respiration and get a lot of ATP made there. Then from that same fat molecule, these 3 fatty acids, you can make many of these acetyl-CoAs. So then that enters here, and you're going to do this part of cellular respiration many times. And so you're going to get lots of ATP made from that one fat molecule. You get way more ATP made from that one fat molecule than you do from that one glucose. Even though glucose starts at the very beginning and moves through, for one glucose molecule, you're only doing this 3rd step, which where you get the majority of your ATP, you're only doing it once. With fat, you're doing it once for the glycerol and many times for the fatty acids, for the acetyl-CoA. And so therefore you get lots of energy from fat, and that's why we don't need that much fat in our diet, which is why we store it in these special cells in our body.
Okay, so I was kind of confused with that acetyl-CoA, like one that you just wrote down from Krebs. Could you say that it goes in a link reaction or the intermediate step, because it's not like necessarily like part of the Krebs cycle that goes in before, or is it just?
Well, when it asked you, let's see here, what was it? With this time of the question, it said, identify the phase of cellular respiration where the molecules would enter the cellular respiration process. So it's entering, that's acetyl-CoA is the molecule that enters the Krebs cycle. All right, it's the product of the link reaction. All right, so it's not entering the link reaction because when the link reaction happens, acetyl-CoA is already there. The link reaction's done. All right, so it would enter in the Krebs cycle. All right, and then as a last resort, what will happen is your body will begin to break down proteins. Proteins, a major source of proteins in our body is in our muscle cells. And so it'll actually begin to break down your protein. This is not a good thing. We don't want our muscles to start to break down. And so what will happen is your protein, which is a chain of amino acids, remember, are broken down into amino acids. This chain of amino acids, once it's broken down, the amino acids can be converted into pyruvate and acetyl-CoA. So the pyruvate here, this is going to enter into the cellular respiration process, not in glycolysis, but it's going to enter into the link reaction. So for A here, when you wrote pyruvate, that enters into the link reaction, or that intermediate step, and acetyl-CoA would enter into the Krebs cycle. All right. Notice that it also produces ammonia. Ammonia is a nitrogen-based compound, and what that'll do is it gets put into your blood, and your kidneys will filter out your blood. And your kidneys filter out your nitrogenous waste, and it actually forms this product called urea, which is part of our urine that we excrete out as a result of your kidneys filtering out your blood. So breaking down protein is your last resort. And so there are actually tests that you can do on urine to tell if a person is breaking down protein. So they actually have little sticks that you can sit in, and it's a color change, and it's testing for the presence of these ammonia nitrogen-based compounds to see if your body's breaking down protein. So for instance, somebody who becomes diabetic, let's say, people with diabetes, they have trouble getting glucose into their cells, and so therefore glucose is used for cellular respiration for energy. And so, this actually happened to my husband. My husband became a type 1 diabetic early in about 31 years old he was. And usually the people with type 1 diabetes get it when they're younger. And so what happened, he was always thirsty. Sign of diabetes, always thirsty, and kept on eating, and was losing weight, and was very lethargic, and so on. And what happened is he became a diabetic. Type 1 diabetes is an autoimmune disorder where your immune system actually attacks your body instead of foreign things, and it attacked his pancreas and the parts of the pancreas that make insulin. Insulin is needed for when you eat and glucose is in your blood. For your glucose to get out of your blood into your cells, you need insulin present. So if you don't have insulin, it doesn't matter how much you eat, that sugar is going to stay in your blood. All that glucose stays in your blood and never gets to your cells. Your cells are literally starving to death. Hence, he started going through this process where his body broke down the glycogen to use it for energy, went to the fat, hence losing weight, all right? And then eventually, your cells are starving, they'll start to break down your protein. And so therefore, a test of that to see if your body's doing that is they can test the urine to see if there's nitrogenous-based compounds, and that's a sign of your body breaking down protein, all right? So you don't ever want to get to that point where the protein is being broken down, all right? And so that's your kind of the flow of energy resources there, all right? So that is number 30A. For ammonia and urea, is there a place where that's used? No. All right, that's excreted, that's waste, that cannot be used in cellular respiration. All right? And then lastly, B, glucose has 6 carbons. A fat molecule could have 10 times that many carbons. Predict the number of ATP molecules produced between a glucose and a fat molecule. Which one's going to have more? The fat. The fat molecule will have way more because of all the places that these molecules can enter, and so they're going to be going through cellular respiration in different parts of it way more. All right. So then, C, can't see C here. Consider where proteins are stored in your body, what types of tissues would be affected, and that is your muscles. Alrighty. So hopefully if you didn't understand this part here, now you understood. I had a lot of people put question marks next to it and all kinds of stuff. Okay. So we're going to move on and look at the last step now. So we have basically all the steps that we've talked about so far. Everything leading up to this is to generate electron carriers. Which, by the way, let's add to this picture. I just realized we didn't write about the Krebs cycle. So when we go through the Krebs cycle, or the citric acid cycle, what do you think the main purpose is for that? We just talked about what it did. What do you think's the big picture here? That's right, to make the electron carriers. What are the electron carriers that are made in the Krebs cycle? Olivia? NADH and FADH2. So I'm going to put another arrow here to the electron transport chain and add on this arrow NADH and FADH2. Let's add some numbers on there. How many of each? 6 NADH. Yep, you're right. One of those is right. It's 2. 2 FADH2s. All right. Each one of these carry 2 electrons. So that's really the whole purpose of the citric acid cycle, the Krebs cycle. In this process, though, we get a little bit more ATP. How many ATP? Remember how many ATP additional? You got 2 from glycolysis, none from the link reaction. An additional 2. All right, so I'm going to put down here 2 ATP again with a little thing here. So 2 ATP, 2 ATP. Again, not a lot of ATP, these 2 ATPs here, to keep the cell alive.
That's created to the cycle.
This is, yes, so the Krebs cycle. I just put it down here.
Is it coming off of it, and like where does it go to the last step?
The ATP?
Yeah.
No, this ATP is used by the cell for energy.
So it like secretes out?
Yes, 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 absolutely. And the last thing that's made as what's the waste product that is up here? The CO2. We lost some CO2 here, and we lose some more CO2 right here. The CO2 is a waste product. We get 4 CO2 as a waste. Notice here 2 and 4, we get our 6 CO2s that are given off in our equation there. All right, so that is the Krebs cycle. So now we have to look at, so far, not making any ATP. So all these previous reactions, really what they are is they're breaking down glucose, molecules that were once glucose, stripping electrons, making these electron carriers. And so by the end of the citric acid cycle, all the electrons and the glucose is completely broken down, and all the electrons are now in these electron carriers. So they're going to carry them to this third step, which we talked about yesterday, consists of the electron transport chain and chemiosmosis. So let's look at the electron transport chain first, because that's what happens chronologically first here, where the electrons are dropped off. Where is the electron transport chain? I wrote this here in the middle of the mitochondria and the matrix. That doesn't happen in the matrix. The inner mitochondrial membrane. So this is why this membrane is folded. So that we can have lots of electron transport chains and lots of chemiosmosis and lots of ATP made. What is the electron transport chain? It's part of the membrane, but what isn't? They're proteins embedded in the membrane. And so when we looked at the proteins,
The inner membrane space?
No, the inner mitochondrial membrane. So let me go back to this picture. I just want to relate it to our notes here. So, so this picture here, I talked about in the video in our notes. So this is the inner mitochondrial membrane, and there's these big protein complexes. And if we look back on here when I first introduced them, here are these big protein complexes. Each complex is made out of smaller protein molecules. And so, and these guys comprise the electron transport chain. So if I draw this up here, on my picture here, I'm just going to put the bigger complexes here. So 1, 2, 3. Notice that there are smaller molecules in between. So here's the 1, 2, 3 protein complexes. And so I'll just draw a couple of different proteins and to link them together. But this right here, this part right here, is the electron transport chain. So let's look at what happens in the electron transport chain. These electron molecules, the electron carriers I should say, NADH and FADH2 are coming and dropping off electrons. So let's look at NADH first. So all of these NADH molecules, I'm going to put here NADH, is going to drop, they're going to drop off the electrons. And the electrons actually move. That's why I put it in a different color here so you can see here. The electrons, and there are 2 of them, so I'm going to put 2E on the line here. So 2 electrons actually go through the molecules of the electron transport chain. So they're transferred from one molecule to the next. Now when that happens, I want to relate this to our picture in our notes. Alright, I'll put this up here so that you can see the connection between what I'm doing and what we did in our notes. When this happens, remember how NADH was made. Let's just review that. NAD plus reacted with 2 hydrogens to become NADH with an H plus left over. So remember, a hydrogen is 1 proton with 1 electron spinning around in it, and there's 2 of those. So remember, one of the electrons went to neutralize it, the NAD, so it's no longer a plus, so that gets rid of that electron. This is now an H plus ion. That's your leftover H plus. Your second H becomes the H on NADH. So therefore, this is carrying 2 electrons, 1 with the plus and to neutralize the plus and 1 in the H. So what happens is when NADH, now we're going to look at it opposite here, when NADH becomes NAD plus again, what does it also release? Well, look at here. When it releases the 2 electrons, all right, one of those was to neutralize it, and one of those was carried in the H atom. So therefore, when we break this down, we're going to have an extra H plus because the electron from the H went to the electron transport chain, which leaves, we take an electron off a hydrogen, leaves an H plus. So therefore, you have, I'm going to put here, an H plus here left over. So, all right, so somebody tell me this. These electrons are moving through the electron transport chain. Do you guys remember why they moved to through the electron transport chain? Why is it that they do that? Megan. Okay, yeah, the electronegativity increases from one molecule to the next. So this one is, this first molecule in the electron transport chain is more electronegative than NADH. So electronegativity, remember, draws electrons towards itself. So therefore the electrons leave NADH and go to that first molecule. But then the next molecule is more electronegative than the other molecule. So then the electrons pass to the next one. And so on and so forth. And so therefore, every molecule in the electron transport chain is more electronegative than the previous one. And so therefore it draws the electrons through. What's the final electron acceptor and the most electronegative molecule that I don't have drawn up here? O2. And this is where your oxygen is used in this. So therefore the final electron acceptor is O2. And that's the most electronegative. And so what happens is, let's talk about these H pluses here. So you have H pluses and you have at the end here, so there's oxygen, and you have the 2 electrons that just came through the electron transport chain. These 2 electrons meet up with 2 hydrogen ions here, the H pluses that are in the matrix here. And an H plus is really just a proton missing an electron, a hydrogen atom missing an electron. So when an electron is added in there, we now have a fully made hydrogen atom. So therefore, we have 2 hydrogens, and it says O2. So our book often uses it says a half of an O2 molecule, which is just as 1 oxygen. And these 2 combined, 1 oxygen and 2 hydrogen, makes a molecule of water. And so therefore, here's your water as an end product here. That's why water is on there. And so that is what happens in the electron transport chain. Is these electrons move through the electron transport chain. Oxygen's role is just to draw the electrons through, and then they create molecules of water, which is your waste product. Water is not the purpose here of this. Also, no ATP is made, so the ATP is not the purpose of the electron transport chain. Can somebody tell me what the purpose of the electron transport chain is that I haven't put on here yet? Purpose of the electron transport chain. What happens? It has to do with the electrons moving through it. That doesn't happen when the electrons don't move through it. Megan? That's right. It pumps H plus ions into the inner membrane space. So these are channel proteins that pump the H pluses into the inner membrane space. When I say pump, what does that mean? It's going from low to high concentration. And so I'm going to write here, low H plus concentration, high H plus concentration. So it's going from low to high, which means that it requires energy. Now when we talked about this before, the energy source usually came from ATP. Guess what? No ATP is used here. So where in the world does the energy come from? The energy comes from the series of reactions when the electrons move through the electron transport chain. When the first molecule gets the electrons, it becomes reduced. All right? When the electrons go to the next molecule, I become now oxidized, the next one becomes reduced. Then the next one passes the electrons over, this one becomes oxidized, the next one becomes reduced. So it's a series of oxidation-reduction reactions where molecules are getting electrons, losing electrons. So what happens is that releases energy when that happens. That energy is used to pump the H pluses into the inner membrane space. So therefore, we always, in our mitochondria, have this high H plus concentration in the inner membrane space. Having that high H plus concentration is very important. Why?
In order to create the ATP, the H plus to back into the inner membrane space. So that doesn't take an ATP, it happens automatically. There's a higher concentration.
That's correct. All right. So these H pluses are going to diffuse back in, and those diffusing back in from high to low concentration is this chemiosmosis part, which is where we're going to make our ATP. Because so far, We've not made any ATP yet, all right? And I will hold off on that to draw that tomorrow for us. I can't stress enough, you guys, of spending time like reading the book and going through this, seeing if you can answer the questions when we talk about it.